Welcome back to Dave Does Math at Home. This is part 2 of our video series on section 4.5, which is about optimization. We're doing calculus to find maximums and minimums in story problems. This is my favorite calculus optimization story problem here. And I definitely wanted to do this one from the beginning. The problems I did in the last video were sort of missing a step because I said the problems out loud with my mouth but didn't write them down, and as I said it I was drawing a picture, and that's not how you're going to get problems on the homework and on the tests. On homework and tests you're just going to get something like this. You're going to get a bunch of words. You're going to have to draw your own pictures. So I want to encourage you right now, that's step 1. Maybe even more important than step 1. That's step 0. Figure out what's going on and draw a picture of it. In this problem, we have Stevie. Stevie is making an open-topped box out of a square 12-foot by 12-foot sheet of metal by cutting squares out of each corner and folding up the flaps. What is the largest volume box she can make? So, step 0, we've got to draw a picture. We have a square sheet of metal, 12 feet by 12 feet. We're going to cut corners out, or we're going to cut squares out of each corner, and then we're going to fold up on these flaps. Once these squares are gone, we'll have like this square in the center and 4 flaps. We can fold up those flaps to make an open-topped box. That's the situation. So the only real variable here that we have control over is how large are the squares that you're cutting out. If you cut out a really, really tiny square, then you have a bunch of area in the middle here. You have a very wide box. But because the size of the square that you cut out determines like the height of these flaps, when you fold these flaps up, whatever size square you cut out becomes the height of your box. It's the height of those flaps. So if you cut out a very small square, you get something that's very wide but very short. And if you cut out a big square, you get something that's taller, but it's not very wide. So that's sort of the constraint that we're working with here. And that's also the variable that we have. So let's start naming things. I'm going to say we're going to cut X feet out of each corner of this thing. X by X foot squares are the corners that we're cutting out. That's the size of what's going missing. Based on that, I need to figure out the volume of this box. Volume is length times width times height. That's the volume of a rectangular prism. Height is pretty easy. If this has length x, or if this distance is x, then when you fold that flap up, that becomes the height of the box. So the height is just going to be x. Perfect. No mysteries there. Length and width are what are going to become sort of problems for us. Length and width. We need to know how much box is left here in the base after we cut away these squares of size x. And that, well, first of all, we know that they're going to be the same, because we're starting with a square and we're cutting squares out, so all of these distances are the same. But we need to connect it to x, because x is the variable that we want to be using here. And the connection to x is, this whole thing is 12, and we're taking x out of one side and x out of the other side to get L. So L is 12 minus 2x. And W is the same. 12 minus 2x. these are our dimensions. So the volume is 12 minus 2x squared times x. This is the equation that I want to optimize. I want to maximize this relationship. I want to maximize the volume. And it's already in terms of only one variable. I couldn't maximize it here because there's 3 variables involved, and that's too many for me right now. We'll get to that in Calc 3, but for now, we need to make everything be one variable. And it is, we just have to simplify it a little bit. So we'll say volume equals 12 minus 2x quantity squared is going to be 144 minus 48x plus 4x squared. That's all still times x on the back end. So volume, I'm going to rearrange it as I distribute this x in here. I'm going to get 4x cubed. I'm going to get negative 48x squared. And I'm going to get plus 144x. This is my simplified volume equation. This is what I need to maximize. This is what I need to take a derivative of and set equal to 0. To do that, I'm going to erase the story problem, just because I'm running out of room. I trust that you're all taking very meticulous and diligent notes as you watch this, so if you need to reference the story problem again, just look at that spot where you wrote it down in your notes, because you're such a good student. Okay, volume is, let me write this again, 4x cubed minus 48x squared plus 144x. And I need to maximize this by taking a derivative and setting it equal to 0. Derivative should give me 12x squared minus 96x plus 144, which kind of feels like a lot. But we can factor this out pretty nicely. We can pull a 12 out right away. Actually, if I'm setting this equal to 0, I can just divide everything by 12. That'll leave me with an x squared, a negative 8x, and a positive 12. So now I need to factor this by finding 2 numbers that multiply to give me 12 and add to give me negative 8. And that should be x minus 2 and x minus 6 equals 0. So I have x equals 2 and x equals 6. At the start of the first video on this section, I was saying we needed to get some answers and then we needed to think about them critically to make sure they make sense. That's going to become really important here because we have 2 answers. Are they both maximums? Is that how this works? Let's think about it. If we cut squares of side length 2 out of each corner, then we end up with a volume where there is 8 feet left in length, 8 feet left in width, and a height of 2. That'll give us 128 cubic feet of space. That's a chunk of cubic space. That's not small. That seems like a viable candidate for a maximum. If we cut squares of side length 6 out of this, if you start with a box that's 12 by 12, and you cut a 6 by 6 corner out here, you cut a 6 by 6 corner out here, and you cut a 6 by 6 corner out here, and a 6 by 6 corner out here, you have no box. You just cut your sheet of metal into 4 squares and then threw them all away, and now you don't have a box. This is a critical point because it is a minimum. This minimizes the volume at 0. This is actually your max, which is what we wanted. We wanted to maximize this volume. X equals 2 is the number that maximizes this volume. So, you need to cut 2-foot squares out of each corner of this piece of sheet metal, and then fold up the flaps to have an 8-foot by 8-foot by 2-foot open top box. That is the most volume you can get out of a 12-foot by 12-foot sheet of metal. That's it for this section. There are other things that I could talk about, but I'm not going to. The beauty of this section is that there's lots of different story problems that you can use calculus to optimize, to find maximums and minimums for, and discovering them and figuring them out is going to be part of the puzzle, and I don't want to take that from you. Good luck. You can do it.